Hello, my name is Bruno. I am a PhD student from Brazil. I will present our paper named Warp-centric K-nearest neighbors graphs construction on GPU. In the paper, we focus on the construction of K-nearest neighbor graphs, or KNN graphs. These graphs represent the K most closest points for each high-dimensional point in a dataset. Today, there are several popular algorithms that require the computation of KNN graphs. Here we give a more formal description of KNN graphs. If we have a set of high-dimensional points x, we can define a function g that returns the neighborhood or KNN set of each point. Each neighborhood will contain k elements, where k is defined by the user. This equation must be satisfied for all neighborhoods. The distance between a point and its furthest neighbor must be smaller than any distance between this point and other point outside of the neighborhood. Some algorithms only need an approximation of KNN graphs. In this case, some neighbors not necessarily reflect the closest points. Our objective in this paper consists in improving an existing algorithm named RSFK. This algorithm computes approximation of KNN graphs using GPU. We have identified the bottlenecks and proposed a new approach to optimize this algorithm. The RSFK algorithm consists in creating and processing several trees. Each tree is constructed by partitionated and high-dimensional space of points. At any given partition, 2 points are sampled and a hyperplane is computed between them. Note that the hyperplane divides the space in 2 new partitions. This process is done recursively for each partition generated by the hyperplanes. This is similar to other techniques like random projections, which requires the projection of all points into a random hyperplane. When the tree is constructed, the leaves are used to update all neighborhoods. All points inside the leaf are candidates to be neighbors. The quality of the approximations depends on the number of trees and the size of leaves, which is controlled by the user. Here we show the execution time of each step of the RSFK executed for 3 datasets and the quality of the result. Clearly, the step where the neighborhoods are updated is the most expensive. Other interesting aspect is that the larger datasets requires more trees to achieve good accuracy. The KNN sets update step will compute the pairwise distance for all points inside each leaf. This distance can be represented in a virtual matrix. Only elements above the main diagonal are required. Each distance is related to a pair of points. After the computation of a distance, the neighborhood of the first element in the pair is updated. Then, we use the distance to update the other neighborhood. One approach to implement parallel algorithms consists in using warp-centric kernels. The usual approach in GPU computing is to use all threads in the CTA to cooperate and perform one task. Other approaches consist in assigning one task per thread. In the warp-centric approach, all threads in the same GPU warp will cooperate to execute the same task. All threads in the warp possibly cooperate using special warp collective primitives and can exchange values in registers. And of course, it's possible for an algorithm to alternate the cooperative strategies used in different phases. In our experiments, we have considered NVIDIA hardware. We designed 3 different warp-centric kernels to KNN sets updates. In each kernel, the warps cooperate in a set of tasks as described here. Most representative tasks is the computation of high-dimensional distance that produce high throughput and avoid sorting operations or the need to maintain heaps. The 3 approaches are the atomic approach, the tiles approach, and the diagonal approach. This later 2 avoids atomic and lock operations. I will explain them in the next slides. The first technique is the atomic approach. The main idea of this and the following approach consists in assigning each leaf to a GPU thread block. The strategy of the atomic approach is to assign each distance to a virtual matrix to a GPU warp. This distance will be stored in shared memory. Then, the threads of each warp cooperate to compute the distance in parallel. This is the idea of the warp-centric method. After the computation of a distance, the warp needs to update the KNN set. It's possible that different warps try to update the same KNN set. To avoid inconsistency, a lock and unlock system is executed using atomic operations. Note that some warps can become idle waiting to unlock, and the atomic operations are slower than regular operations. This can lead to poor performance. To overcome this limitation, we propose two approaches that do not use the atomic operations. One of them is the diagonal approach. In this approach, each diagonal of the matrix is computed at a time. Each distance of the diagonal is assigned to a warp, following the warp-centric method. Note that there is a pattern in the index for both elements of each pair. In the image, we can see that the rows represent the first element of each pair and the columns represent the second. There is no distance in the diagonal that shares the first or the second element of each pair. If we perform the update of the first element before the updates of the second, we can ensure that there will not be any concurrent access. This is performed using zipper barrier synchronization. The second proposed technique is the tiles approach. In this approach, we divide the virtual matrix in tiles. Each tile will be computed at a time, similar to the diagonal approach. Each warp will compute all distance of a row in the tile. After the computation of the distance, the warps will follow a pattern to update the KNN sets. First, each row is assigned to a warp. In the tile, each point index is related to a row. For this reason, each warp can update the KNN set of that point using the computed distance. After this step, there is a synchronization barrier. Then, the same is done for the columns which are related to the second elements of the pairs. With this arrangement, it's possible to say that there will not be concurrent access in the KNN sets. Also, note that the warp will follow an execution where the same variables are reused. This can create better memory access pattern and lead to better performance. To perform our experiments, we have used 3 real datasets, each one with different number of points and dimensions. We also have used artificial datasets generated using random sample for random distributions. These artificial datasets have different number of points and dimensions, and were used to execute the algorithms with different values of k and the leaf size. We have executed the files library to create KNN graphs of these datasets, which is a popular library to perform similarity search using GPU. We also have executed RSFK using nearest neighbor exploring, or NNA, which is a post-processing technique that can be applied to RSFK and it's better described in our paper. The 3 designed methods and the files library were compared using RTX 2070 GPU. The first analysis, we compared the 3 kernel implementations for each design approach. It's clear that the diagonal approach had the slowest execution and the tiles approach was the faster method. And we also have executed the tiles approach considering different size of tiles. As you can see in the image, it had a small impact. In these charts, each marker represents a complete execution of an approach for artificially generated dataset. Each execution has one variable parameter, and the others are fixed. In the left figure, you can see that the tiles approach presented the best behavior, better yet with the increase in the number of points. However, as you can see in the right figure, the other approach had equivalent results for datasets with small dimensions. When you analyze the impact of the value of k, our approach surprisingly maintained their execution time. This can be explained considering that our approach avoids sorting the neighbors by distance. However, the users of the algorithm should be aware that the value of k will determine the size of the output, which can be a problem for low memory GPUs. The figure on the right presents the impact of the size of the leaves for each approach. The behavior is similar for all of them. However, it's clear that the tiles approach was the faster in general. It's important to remember that the larger size of leaves are desirable to improve the accuracy of KNN graphs. Finally, we have compared the RSFK with files library in GPU. The execution of RSFK is using the tiles approach because it was the fastest, as I have commented in the previous slides. Each marker in the figure represents an execution of each algorithm using different values to control the trade-off between execution time and KNN graph accuracy. The number of trees is used to control the quality of RSFK, and a parameter named anyprobe to control files. We can see that we can achieve up to 639% speedup over files. Also, it's possible to see that the nearest neighbor exploring allows better speedups at higher values of accuracy. In conclusion, we have identified the bottleneck of RSFK algorithm. We have identified that the warp-centric method was the best strategy to implement the KNN sets update kernel. The design tiles and diagonal approach would mitigate the problem created by using atomic and lock operations. The tiles approach was the best method and presented better results for datasets with higher dimensions. We also have identified that the execution of these methods can be compute-bound or memory-bound depending on the considered scenario. There are other analysis and profiling results in the main text. The next steps of this work could include using multiple GPUs and using intelligent strategies to choose automatically what kernel implementation will be used. Also, it's possible to apply the contribution of the proposed methods in other applications like dimensionality reduction and clustering techniques. Further analysis using different GPU architectures also will improve our understanding of the behavior of all compared approaches. This was what I have for my presentation. I would like to thank you for your attention and also thank our sponsors. If you have any questions, feel free to contact me.